Now that we have an understanding of Hess's law, we're going to see that the properties of delta H are especially useful for several reasons. And let me enumerate those here. So properties of delta H. And I'm going to also specify that what we're after is the delta H of a reaction. So that's what this subscript R means. Okay, first of all, the delta H's can be tabulated. So we can tabulate delta H for several reference reactions. So I'll say for reference reactions under very well controlled or standard conditions. All right, what this will do is give us sort of a reference set that we can use to then, with Hess's law, find the delta H's for other reactions that might be of interest. And so that actually is the second property here, is that these can be combined. All right, so what we're looking for is a way that we can compile some information so that we could actually predict the enthalpy change for any arbitrary reaction simply from looking up values in a table and combining them in the right ways to get the number that we want. And so that's what we're really after. So we can combine these reference reactions, and we'll discuss in just a moment what those reference reactions might be, to find the change in enthalpy for any reaction. Now, of course, there are limits to that as well, because it's possible that you may not have information about some exotic chemical that you need in a reaction, but for many reactions we can do this. All right, third, we can adjust for different phases. And I'll say something at the very end of this video very briefly about this, but the fact is that the enthalpy change for a reaction depends not only on the nature of the composition of the reactants and products, but also on the phases that they're in. Okay, so we'll be able to adjust for different phases using the latent heat of vaporization, for example, or the latent heat of fusion as needed in order to convert those things to other phases. All right, now finally, we can extend these results to other values of temperature and pressure that may not be part of these standard conditions that I've cited up here. All right, so that's what our game plan is. We want a way of tabulating information so that we can easily make a prediction about the enthalpy change of a reaction without actually running the reaction. That would be a theorist's dream. All right, so in order to do this, I want to define standard conditions. And these are the conditions under which we're going to assume that all of these reference reactions are going to be taking place. These standard conditions will consist of a pressure of 1 bar and a temperature of 298 Kelvin, okay, roughly room temperature. So in other words, we're going to tabulate information that is specific to these conditions and use that information to construct reactions and then evaluate what the enthalpy change of reactions is under those same conditions. Now, in order to do this, I'll need to define standard states. Okay, and these apply to both elements and compounds. But essentially, the standard state of a substance is the most stable form of that substance at standard temperature and pressure. All right, what do I mean by that? Well, for example, oxygen is a gas at this temperature and pressure, so that would be its standard state. Carbon, on the other hand, is a solid. However, it has several different forms of solid, and in fact the most stable one at this temperature and pressure is graphite, not diamond. So what this means basically is that we would define the standard state of carbon, solid, as graphite. All right, the difference isn't great, but it is nevertheless a difference. Now, in order to do this, we're going to need to establish some kind of reference reactions. These are going to be the reactions that we tabulate and tabulate the delta H changes for, so that we can add them together in such a way as to create all sorts of new reactions. Now, there's nothing that limits what we can do here, but what we want to do is to put something together that is going to be the most flexible and the most useful for widespread use. So, in fact, the reference reactions that we tend to put together are the ones that involve the synthesis of a compound. So, synthesis of a compound from its elements, but its elements at their most at their standard conditions, their standard states. All right, what this represents is a, if you will, a reaction of formation. We call these formation reactions, and the enthalpy change that accompanies these reactions is called a heat of formation. And we give it a special symbol. We give it the symbol delta FH0. Now, let me unpack this a little bit. The delta, of course, is for a change. F is for formation. So whenever you see the subscript F here by the delta sign, we're talking about a formation reaction or a heat of formation if the change is a change in enthalpy. The 0 up here is simply indicating that we are at a standard condition or a standard state, the standard states in this reaction. So there is meaning in every symbol that's used in this particular designation for heat of formation. All right, let me just give you a quick example. Let's suppose that we're interested in the synthesis of acetone from its elements. Okay, so acetone, many of you know this already, is simply this compound. It's a ketone, very simple, I guess the simplest ketone, and it has a formula C3H6O. So if we were going to compose 1 mole of this from its elemental substances, what elements does it have? Well, it has carbon. Okay, so we would have carbon as a solid. We would have 3 of those, so I need to multiply that by 3. I would have H2 for the hydrogen. I need 3 of those also. And hydrogen is a gas under these conditions. And then I have oxygen. Now, oxygen normally at its most stable state is oxygen diatomic molecule. So I only have 1 oxygen here, so I'm going to have a half mole of oxygen molecules to give me the oxygen that I need. And then this would be brought together somehow magically to form acetone out of this. And acetone is a liquid under standard conditions. So we've got solid, gas, and liquid all together in this one equation. Now, if we were able to somehow miraculously put this reaction together in the lab and do it under very controlled circumstances, all of this, assuming that the initial and final states are under standard conditions as specified up here, then we would find that the enthalpy for this reaction, which would be the enthalpy of formation for acetone, so I'll indicate that here. All right, that enthalpy of formation would be negative 249.4 kilojoules per mole. Okay, so that means for every 1 mole of acetone that I would produce from this sort of reaction, this would be the enthalpy change, negative 249.4 kilojoules per mole. All right, so if, for example, I don't like having just a half mole of oxygen molecules and want to have a whole mole, then I would be creating 2 moles of acetone, and I would have to double this because delta H is an extensive property. All right, so what we find in practice is that the heats of formation of all kinds of compounds, like acetone and like anything, are basically tabulated together in thermodynamic tables. And you can find one of these if you go under the course resources on the left margin of our course site. You'll find a link to standard thermodynamic quantities, and that will give you a list of compounds. It's not a comprehensive list, but it does have a lot of compounds in it. And you can look up their delta H of formation, their heats of formation. All right. Now, one thing I need to point out in all of this is that if I have an elemental substance, so elemental substance like oxygen, how would I form a reaction of formation for oxygen? Well, that one would be pretty simple. It would just look like this. And since I have the same thing as a reactant and as a product, the heat of formation for oxygen in this case is simply defined as 0. Well, in fact, this is defined this way for any elemental substance. Since the reactant has to be the same as the product, we're going to have, by definition, an enthalpy change of 0 for the heat of formation of that. All right, now what I want to do is I want to show you how this works in practice for a real reaction. So in order to make sure I have plenty of room, I'll put this on another page. But what we'll be looking at is the combustion of methane. And this is essentially the reaction that you're probably doing in your house or your apartment now to provide heat. Well, maybe you're not doing it now, but you will be in a few months to provide heat. Methane is the principal component in natural gas. So the combustion of methane is how we heat our houses. All right, so let's get to a new page and work this out. So the combustion reaction of methane would look something like this. Have methane as a gas, which is its standard state, and then it would be reacting with oxygen gas, and it will form carbon dioxide gas. And for now I'm going to say that the water that it produces is a gas. That probably is true in your heater, but one could also imagine circumstances where we would create liquid water. Okay, now this is not a balanced equation. In order to balance it, I would need to put a 2 here and a 2 here, and that's going to affect our enthalpy change in the end. Now, what I want to do is I want to reconstruct this equation using a bunch of formation equations, formation reactions, so that I've got my products on the right-hand side and my reactants on the left-hand side of the equation. So I'm going to start with products first, just because that'll be a little bit easier. And the first one I'll do is carbon dioxide. So the formation reaction for carbon dioxide would be carbon solid, which was graphite, plus oxygen gas forming carbon dioxide gas. And what I would find is that the heat of formation, oops, let me make a little F there, heat of formation for carbon dioxide is negative 393.5. Okay, the next product is water as a gas. So in this case, I'm combining hydrogen gas and oxygen gas to make water. And I'm going to specify that as a gas. And in this case, I'm only making 1 mole of the water, so the heat of formation in that particular case is going to be minus 241.8. Now, I know that in my balanced equation I have a coefficient of 2, so I'm going to register with you right now that ultimately I'm going to have to multiply this whole thing by 2. And that includes the enthalpy, because enthalpy is extensive. So I want to make that note here before I get on to reactants. Okay, now as I consider the reactants, what do I need to do? Well, the reactants are on the left-hand side of the equation, but the way we normally write formation reactions is with the product as the thing that we're interested in. All right, well, since these are on the left-hand side, I'm going to have to reverse that reaction. So in this case, if I write my reaction as CH4 gas reduced to carbon solid, which is graphite, plus 2H2 gas, all right, this is the reverse of the heat of formation reaction. So what does that do to the heat of formation, the enthalpy of formation for that process? Well, in that particular case, the enthalpy of formation is going to be the reverse. So delta H of this process is the negative of the heat of formation for methane, so it'll be plus 74.6. Okay, but register that I had to make the minus of this quantity. All right, what you would find if you look in the table for methane is that it's negative 74.6. All right, my last reactant is oxygen, and oxygen would have a formation equation, as I've written before, where I just have the same thing for reactants and products. So this is not going to contribute at all, won't contribute. And I'll note that it won't contribute either to the enthalpy change, nor will it contribute to the net reaction. If I add these reactions up, I'll have to cross off everything that appears on both sides of the equation. Well, those appear on both sides of the equation, so they would be gone. But notice that I'll get one oxygen from here, and I'll get another oxygen from here to give me the 2 that I need in the net reaction. And in fact, what you will find is that when you add these equations together that represent the formation reactions, that the elements will all cancel except for ones that have to be there for the net reaction. So the carbons solids cancel. The H2s, 2 of them here, 2 of them here, they will cancel. And so in the end, our net reaction will be exactly the reaction that we want up at the top. All right, so I will have CH4 gas plus 2O2 gas going to CO2 gas and to H2O gas. Okay, exactly the net reaction that I want. But now I know that to get the delta H for this net reaction, it's got to be the sum of the delta H's for the various steps that got me there. So the delta H for the reaction is going to be negative 393.5, and then I have to double this one because I multiplied by 2, so that's going to be minus 483.6, and then I have to add 74.6. All right, so the net result of this is negative 802.5 kilojoules per mole is the heat of reaction for methane under standard conditions. I want to emphasize that this is under standard conditions, not under different conditions. So if you would rather have the heat of reaction under a hotter temperature or a colder temperature or under a different pressure, then we'll have to do something else, and we'll talk about that in a different video. Now, the other thing I want to explain here is what would happen if instead of having water as a gas, I had water as a liquid. Well, if I had water as a liquid, I would find that the heat of formation for water as a liquid, so I'll write it like this, would not be negative 241.8, it would be negative 285.8. So you can see that because this is different from this, I'm going to get a different enthalpy of reaction. So it matters what phase your substances are in, and you have to pay attention to that and pay attention to the way they're listed in the standard tables of heats of formation, because it will change the heat of reaction if you use the wrong phase in your calculation. All right. If you have any questions about this, you may want to go back and consult your general chemistry notes, because I know this is something that is often taught in that class, and I hope that none of this has been especially new for you, but simply something to jog your memory.